Recording in progress.
Hi students, in this lecture we are going to learn how to calculate electric field inside a non-conducting sphere which is uniformly charged. That is given now volume density rho. Let us see how to calculate. So it is given that distribution of charge uniform and we have to calculate inside the sphere. So taking one sphere. So here distribution of charges in the entire volume. It is in the entire volume. Okay. Now we want to calculate at some distance r from the center. Given that distribution of charge is uniform in the entire volume, that is rho. So now we have to calculate this by using Gauss law. So first what we are doing is imagine one Gaussian surface that is now sphere. By taking now this distance as radius, so imagine one sphere by taking that distance as radius, right? So here we can guess that by symmetry, field will be radially outwards. That means at each and every point on the surface, field will be normal. At the same time, if you consider a small area on the surface, for that small area vector, direction will be radially outwards. That means at each and every point on the surface, angle between E bar and ds bar is 0. See here what we can write from Gauss law, closed integral E bar dot ds bar equal to net charge inside by epsilon naught, right? So here at each and every point, modulus of E bar is the same and between these two vectors angle is 0. So what we can write here, it is E into 4 pi r square, that is equal to 1 by epsilon naught. See in the place of charge what we can write. Since distribution of charge is uniform, we can write charge will be equal to, if, see what we can write here, rho into corresponding volume is now 4 by 3 pi r cube. See carefully once. Rho is now charge per unit volume into this corresponding volume. Okay. That is now giving us charge inside the Gaussian surface. Now here 4 pi gets cancelled, r cube and it is r square. So remaining is now E bar equal to, if I am taking in vector form, what I can write, what else left here, 4 pi over, rho is left, 1 r is left here and 3 epsilon naught. So I can write this as rho by 3 epsilon naught into r bar if you take in vector form. Okay. That means the field is radially outwards, right? Which is a proportional to distance between the center because remaining is a constant. So this is now field when we are taking R is less than or equal to capital R. Okay, where capital R is radius of the sphere. And if you are taking outside, it will be equal to k q by r square, where capital Q stands for charge of the entire sphere. Okay, so this is same as due to a point charge. So the last class we have seen that in case of a hollow sphere, when we are taking field outside, that result was like due to a point charge. So whenever taking outside, we can assume entire charge at its center. So result will be just like due to a point charge. That is what we have written here, kq by r square. Okay. If it is inside, then rho by 3 epsilon naught into r bar in vector form. And what's the value of capital Q here? If you want capital Q, that is equal to rho into 4 by 3 pi r cube. Okay. Right. Now let us focus here. The graph between E bar and distance from the center. So how graph comes? Let us plot the graph. Strength of the electric field taking the modulus value and distance. So here what we can say, R equal to 0, field is 0. Okay. It is now changing linearly with the distance. So I'm drawing it passing through origin. It is linearly. Actually, diagram should be, it should be straight, okay, straight line. It should be straight line passing through origin. It is up to R equal to R. Means up to surface it is changing linearly. And after that, it is just like due to a point charge, graph will be like this. Okay. It is E proportional to 1 by R square. So here E proportional to 1 by R square. Okay. That is a graph for strength of the field as a function of distance. Okay. Let us now calculate potential due to this sphere. See how to calculate potential. So to find potential, we have to consider dV equal to, we are having E equal to minus dV by dr, right? Now from this, what we can write, dV equal to minus E into dr. Now integrate this. See here limits. We want to calculate at a distance r from the center. And let us say on surface potential, it is Vs on surface. That means R equal to capital R. Okay. We want to calculate at a distance R. So this is now upper limit is R. Then see what we get here. Minus integral in the place of E. In the place of E, what we can write. If you want to calculate in terms of charge, see what this result becomes now. Rho by 3 epsilon naught into R. That result becomes now, same thing becomes, I will write here, that result becomes now E equal to K Q by R cube into R. So how we got this means in the place of this row, substitute now Q by 4 by 3 pi R cube. I am repeating, in this place, in the place of this one, write Q by 4 by 3 pi R cube. Then we get K Q by R cube into R. Now substitute this in this one. It is K Q by R cube into R into dr. Okay. So this is now V minus Vs, that is equal to minus, you can take constants outside, K Q by capital R cube. Remaining is now integration of R dr. It becomes R square by 2. I am taking 2 outside, R square by 2. It is R square minus R square. Okay. Upper limit is small r and lower limit is capital R, right? Now here potential on the surface. Potential on the surface means it is simply same as due to point charge kq by capital R. This is what we have discussed while taking potential due to hollow sphere, right? On the surface kq by capital R, outside same as due to point charge. Now substitute this value in this one, then we are going to get, by substituting this value in this one, we are going to get, it is, see what we are going to get, kq by 2r cube, kq by 2r cube into 3r square minus r square. This is what we are going to get after taking this value in the above one. Okay. This is a potential inside the sphere. And if you see here carefully, when R equal to 0, potential is not 0 at the center. Okay. So this is a way of calculating electric field and from that potential. Right. Let us see now questions basing on this. So this is a question taken from IRODOV basing on the same derivation. Now what we have done. Inside a ball charged uniformly with a volume density rho, there is a spherical cavity. The center of the cavity is displaced with respect to the center of the ball by a distance c. Find the field strength E bar inside the cavity, assuming the permittivity equal to unity. So given there is a ball, distribution of charge uniform, given volume density rho, there is a spherical cavity. The center of the cavity is displaced with respect to center of the ball by a distance c. So we have to find field strength in the cavity. So how to use the result? Now we have derived in this one. So the result what we got, field strength inside we got E equal to rho by 3 epsilon naught into R bar in vector form, right? So we are going to use now this result in this problem. Now we can say This is now bigger sphere. Inside that, there is one cavity. Cavity means there is nothing inside. Okay, there is a cavity. Let us take now. This is a cavity. Center of that is at a distance C. Okay, that is what given. Okay. Now, if you observe, this cavity can be taken as this bigger one is made up of charge density plus rho. Assume that there are two spheres. One is bigger one and one is smaller one. Bigger one having density plus rho and smaller one having density, it is minus rho. So when we combine these two, then we are going to get a cavity. I am repeating. This cavity can be taken as combination of two spheres. Bigger one having density plus rho, smaller one having density minus rho. Now, when we combine these two, that overlapped region becomes a cavity. It is the overlapped region becomes cavity. So, in that region, we have to find the field strength. Okay. So, I will make the diagram once again clearly. So this is now that cavity. Okay. This is now that cavity. Let us take now this is center of the bigger one. And between these two distance equal to A. Okay. The distance is given as A. Right. We want to calculate now strength of the field at a point. Right. Okay. Let us do one thing. We want to take somewhere here, strength of the field. So here what I am saying is this can be taken as a combination of fields due to both spheres. Let me write here because of the bigger one. See its position vector. So take it as it is R1 bar. Position vector of that point with respect to center of the bigger one. It is R1 bar. Let us take position vector of that same point with respect to center of the cavity is R2 bar. Okay. And let us call this as it is A bar. Okay. This is A bar. So here we are finding field inside the cavity at one point. Then what we are doing is we are finding field due to bigger sphere, next due to smaller sphere. Then we are going to take resultant of those two. Let us call due to bigger one, field is E1 bar. Then it can be written as rho by 3 epsilon naught into R1 bar. This is a field due to bigger one at that point. Okay. Next, field due to smaller one. Let us take it as E2 bar. And E2 bar equal to minus rho by 3 epsilon naught into R2 bar. So we got field due to first one means due to bigger one, field due to smaller one. Now if we take resultant of these two vectors, then we are going to get a field at that point. Okay, means in the cavity. Then see how much we get. So E bar equal to, it is E1 bar plus E2 bar. That is equal to rho by 3 epsilon naught into R1 bar minus R2 bar. Okay. And you can see from the diagram what is the value of R1 bar minus R2 bar, right? So that implies E bar is equal to, see what we can write? R1 bar, I will write here. It is R1 bar. Next, minus R2 bar, minus R2 bar, minus A2 bar equal to 0 bar. Okay. R1 bar minus R2 bar minus A2 bar equal to 0 bar means writing vector equation for the given diagram. So from this we can write in the place of R1 bar minus R2 bar, it is A2 bar. Sorry, it is A bar, right? It is A bar. That means it is equal to rho by 3 epsilon naught into A bar. See what is the meaning of this? In this, rho is a constant, epsilon naught is a constant, modulus of A bar is a constant. Means magnitude of the field at any point inside cavity is same. I am repeating, magnitude of electric field is same at any point inside cavity. Next, what about direction part? Direction is from center of the bigger one to center of the cavity. So at any point inside the cavity, direction of field is along from center of the bigger to center of the cavity. That means E bar is a constant at any point inside the cavity. Means E bar is a constant. So field is uniform. What is it? Field is uniform. Okay. And you can see, basing on this point, two times questions are asked in previous IIT. Let us see now those two questions. They are asked two times. Right. This is in 2007, asked for 3 marks. Spherical portion has been removed from a solid sphere having a charge distributed uniformly in its volume as shown in the figure. Means you can take same diagram, okay? Now what we have explained, the electric field inside the emptied space means in the cavity. So what we got, it is uniform, okay? So answer is now non-zero and uniform, okay? So 2007 asked for 3 marks. And again, same question asked. See the next one. In 2013, again, same question. Two non-conducting spheres of radii R1 and R2 and carrying uniform volume charge densities plus rho and minus rho respectively are placed such that they partially overlap as shown in the figure. At all points in the overlapping region, okay, I will make a diagram here. So it is again the same problem. It is sphere 1 and sphere 2. Density plus rho, here density minus 2. So overlapped region means it is nothing but cavity. What is it? Nothing but cavity. Okay. So in this overlapped region, what is now field? Okay. So again, the same problem, right? See options. The electric field is zero. That is wrong. Electrostatic potential is a constant. So here we got electric field is non-zero. Electric field non-zero means potential is changing. Okay. So option B also not correct. Next. The electrostatic field is a constant in magnitude, and that is correct because we got rho by 3 epsilon naught into A bar, right? The electrostatic field has the same direction. Okay. She's asking at all points in the overlapping region. At all points. At all points, same magnitude and same direction. So answers options are C and D. So ask same concept two times. Okay.